So we talked about electric fields, right? And just to remind you, if you have a positive charge, it's gonna generate an electric field. It's like wind blowing out. So it doesn't have to be a point charge, but any conductor, positively charged, you're gonna have an electric field, right? And the electric field will be out. If you put a negative charge in the electric field, what's going to happen? It's going to be attracted, or it's going to be pushed away from plus, but it's going to move with the electric field, right? So typical conceptual equation for the test, if you have a positive charge inside an electric field, it's going to follow the stream of the electric field, right? What is the electric field? Here you have 1 coulomb of charge. The magnitude of the electric field will be the force acting on that 1 coulomb of charge. It has a magnitude here, but it also has a direction. Is that clear? And remember, it obeys inverse square law. Should quiet. Inverse square law. So if you multiply the distance by 2, the electric field will be divided by 4. Inverse square law, right? If the distance is multiplied by 3, the electric field will be divided by 9. That will be for a positive charge. You see, as I move the positive charge. Here, the electric field is also moving. Now, if I have a negative charge, now the electric field is how? Inward or outward? Inward, right? So a negative charge or a negative a conductor negatively charged will be like a sink. It's sucking the electric field in. Now, if I have a 1 coulomb of charge, it still wants to go with the electric field toward the negative. Now, if you have an electron, it's going to be the opposite. A negative charge always goes against the electric field, right? It's like a critical mind. It wants to go against mainstream. Okay, so we talked about the Faraday cage. Any conductor, if it is charged, the charge always move on the outside. So if you are a conductor, because you are all juicy, right? 80% is water and full of electrolyte. If you get charged because you rub your feet against the carpet, for example, all the electrons are going to move inside your body, but it will stay only on the outside. It cannot be inside. It cannot build up inside because you will be like a Faraday cage. So any conductor, the charges always stay on the outside. It's going to spread out as far as possible. So inside the conductor, the electric field is always 0. And there is lightning outside. If you stay inside your car, you're going to be safe. Except if you go out and you touch the chassis of your car and you put your foot in the water, that might be bad. Otherwise, everything is good.
Because the car is suspended by the rubber tire, that stays charged.
So they're very good, yes. They are isolated. So if there is lightning striking the car, it's going to be charged and the charge cannot escape. So yes, it's going to stay charged. Except some truck, for example, you see some truck, they have like a something coming that will touch the floor, right? Like a string, a conducting string that will be dragged behind the truck. That will be to discharge the truck, right? Like sometimes you have, don't know what it's called. Do you know what it's called? No, it's like yeah. So you have a truck here, and here they have something behind because that way it touches the ground. So if there is too much charge here, maybe not from lightning, but just from friction, it cannot accumulate. You don't want that to be accumulating too much, so the charge can go to the ground if it touches the ground, right? So you have some metallic strip touching the ground, so it doesn't build up too much. Likewise, when you put oil, for example, in an airplane, you have the nozzle here, and there is a strip here, a metallic strip maybe touching the ground. So if there is too much charge, it will go and be grounded, because you don't want to have too much charge on one side, a lot of charge on the other side, then you can have a spark, and that will not be good. Okay, so this is called a Faraday cage. You have that in a science museum. They have those very cool demonstrations. You can have spark here, so it's a breakdown of the electric field. That means you have built up so much voltage here, maybe 10,000 volts, and this is grounded, so that's 0 volt. So the voltage is so big between this part here and that part here that you're going to have a breakdown. Okay, so it's going to be discharged, but it cannot go inside. It will stay outside and then it will go underground. So inside the cage, you're going to be safe, except he's wearing those special ear plugs, so because it makes a lot of noise when it's discharging. Same thing here. You can you won't have connection. So if you try to look at your phone, nothing will happen because it's a Faraday cage, so cannot get the electromagnetic waves. But you will be shielded. So it's like a shield. It doesn't have to be plain here. It can be with holes and like a grid, but it's called a Faraday cage. Is that clear? So you can have what is called a dipole. So you have a plus here and minus here. And I think there was a question on the pop quiz. So if you take a positive charge here and a negative charge here, that's going to be a dipole. And it's important for chemistry because the water molecule is polarized, for example. Here will be the two hydrogen and here it will be oxygen. So it's permanently polarized. Okay, one side has a plus, the other side has a minus. In between, you see that you have the electric field lines. The electric field always goes from plus and up on minus. Okay, so you might ask, where is my plus here? My plus will be the ground. Plus to the minus, plus to the ground. Okay, so it always starts from plus and up in the minus. You see that if you have a bisector here, if I take a line here perpendicular to this line, the electric field is horizontal to the right. Okay, it's not at an angle. I think there was a question like that. That's how an electric field works. And you can think of that, thank you, as it's like a spring that has been stretched out. And the electric field here wants to bring those charges together because now they have a high potential energy and they want to decrease the level of energy of the system. So the electric field here is trying to bring those charges together. So this is called a dipole. Now, if you have two charges and they are like charges, so they are the same. So there was also a question about that. So plus and plus. Now, the electric field is going to repel each other, right? So you have a sensor here. It's going to be repelled here, repelled there. What's going to happen at the center? 0, very good. You have the electric field just at the center here will be 0. Because remember, electric field is a vector. You need to add the vectors to find the net vector, right? So you have a force from this one pushing to the right, and then you have the force from that one pushing to the left. They're going to be equal to each other, and it's going to be 0. Okay? We had a question like that. Like if I take, instead of having one charge, I have two charges, so this one is stronger. Maybe I take 3 charge. So there is a place now where the electric field is 0, but it's not going to be at the center. We did that problem together last time. So here, if you have 3 coulomb, and here you have 1 coulomb. You see that distance here will be 1/3 of the whole distance here. We did the math last time, but you see the electric field here is going to be somewhere, it's going to be 0. Is that clear? And you see the electric field here is going in, this one is going in the opposite direction. So you see that here, right? So when the charges are the same, it's the opposite. It's like it's a compressed spring that want to push away the charges to lower the potential energy, right? So before we keep going, I did another investment for you. Can you see here?
Yes.
Okay, look what I have. It's a plasma ball. Do you see that? It has plasma inside, and inside you have a coil. It's called the Tesla coil. So I'm gonna reach very high potential. So I'm gonna plug that into my computer. Now, do you remember how much voltage do I get from the computer? I think I showed you that last time. Not 12 volts is from the battery. 5 volt. Like when you are charging your phone, you need 5 volt. Is it AC or DC?
DC.
DC. The laptop doesn't like AC. That's why we have a charger. Exactly. But this one is DC. And that was the genius of Tesla. He found a way to produce very, very, very high voltage just with DC. This is a Tesla board. So why do I like it? Because what you are seeing here are the electric field lines. At the center, you're gonna have a very high voltage, right? And what you see here are the field lines. Oh, today. Okay. Can you see it if I do this? So you see here, you have the electric field lines here. You see how they come radially from the center. You see how the lines are very packed together at the center, and they move away from each other as they move further away. So that's because when the lines are close, that means electric field is very strong. As they move away, they're gonna weaken. Do you see that? So what's happening inside? You have a breakdown of the electric field. It means the voltage is so large that the plasma inside get ionized. And the electrons that have been ionized inside the plasma are going to be pulled by the electric field. So it's like current. So if I touch it, can I say that I am at the same voltage than the plasma ball, than the ball here? Yes, I am, because I'm a conductor. So this is 1,000 volts. Okay, so I am at 1,000 volts. So it's a very high voltage. Remember, we have only 120 volts here. So how come you still have a physics professor? Because the current is small. Very good, because the current is small. Remember, from last unit, energy is voltage times current. So even though the voltage is very high, you don't have enough current to kill me. And remember, it's the current or energy to kill me. It's the current that kills. Okay, it's not the voltage. So I do have current going through me from my finger to the ground, because that's what they want to do. They want to go to the ground, but I'm not dead. Okay, so it's a great demo to see to visualize the electric field. Oh, you see that better? So is there something that surprises you? Because this is 5,000 volt. No, not 5,000. 5,000 will be the big one. This one is cheaper. Okay, it's 1,000 volt. So is there something that is weird? I have 5,000 volts here, right? So what did I say just before? Well, was
No sound.
okay? No, there is no sound because it's will be in, sound will need like a medium, right, to propagate. So I don't know in plasma, but something else is weird. 1000 volts here, right? Where is this connected? Okay, how much is the laptop? 5 volt. So what's happening here between 5 volt and 5000?
Huge drain.
Huge step up, right? Multiplied by 1000. That's called the step up transformer, right? So inside you have two coils, a primary and a secondary. And so the voltage is stepped up, but energy is always conserved. So if the voltage is stepped up, something has to go down, right? And what is it that is going down? The current. Very good, right? Energy has to be conserved. So if you step up the current, the voltage, the current has to go down. You can do the opposite, okay? You can step up the current and the voltage will be stepping down. So when you are producing electricity from a power plant, that's what you are doing. You are stepping up the voltage to 100,000 volts. The current will be very small, which is very nice because that's the current that will dissipate energy inside the wire so you don't lose so much money. And once you get to marine biology, you're going to step down the voltage from 100,000 to 120 volts. Okay? So that's the genius of Tesla. He figured out a way to step up voltage without using AC, just with a DC power supply. And he did that using a capacitor. So we're going to learn about capacitor next. It's just a device to store charge and then to burp out charges in a very small time in a huge surge, right? So a capacitor, we're going to learn that next. It's going to burp out very high amount of current during a very small amount of time. Okay, so you can, so it's a Tesla coil, exactly the one that you have if you don't have an electric car and you have a gasoline car like I have, you have something called plug, a spark plug. You know, the plug that makes the spark so you can start burning fuel. That's how it works. It's a Tesla coil. Isn't that amazing? Okay. And then here I have a light bulb, but it's a fluorescent light bulb, right? So it needs very high voltage. So you apply a very high voltage. Electrons inside are being pulled, right? So they're going to accelerate. They're going to bump into mercury atoms, okay? Because they bump into mercury, it's going to emit UV. UV will be absorbed by the phosphorescent coating inside and it's going to emit light. Okay, but my point is that for this to work, you need to apply a very high voltage. So if I hold that here, my hand is at what? What's zero? Very good, because I'm grounded, right? So if I touch it here, that's going to be 1000 volts. So what do you think is going to happen? Oh, you see that? Now, do you see light beyond my hand? No, because the electrons will move from here to my hand to the ground. If I put my hand here, then everything will lit. Isn't that crazy? Crazy cool, right? Yeah, you live a crazy time because those things were not available for so cheap. Okay, I paid $15 for this one and the small one. The big one are $30. It's not so much for the money, but no, when it get big, you know, it's hard to handle. This one is $9, and look, isn't that cool, right? When I was your age, long time ago, we didn't have all those gizmos, so you can try that after. But what I like about that is that you can visualize the electric field. So the electric field is a real stuff, okay? Even though you cannot see it with your eyes, it exists. Okay, let's go back to here. Hello, hello. Yes.
Others is whatever it is.
Plasma.
No, the thing that is the voltage. How does that work?
The coil. It works like what you have in your car. So it's what is it called already?
Plug.
Spark plug. Thank you. So the battery here is going to charge a capacitor. Okay, so what's a capacitor? It's that's what's going to come next. It's a device that can store charges, right? So for example, I'm not taking a tangent because that's going to be the next unit. So for example, you have a defibrillator, you apply a voltage, so you are doing work. So you separate the charges, right? So one charge will be plus, one charge will be minus. So between them, you're going to have an electric field. That electric field is very upset. It wants to bring back the charges together, okay? But it can't unless you discharge your capacitor. So in that case, the capacitor is going to burn out a huge amount of current through your heart, which is the load. So it's like a load, a huge amount of current during a very small amount of time. Because remember, you have a plus here and a minus. So each time is like a potato clock, a potato battery, you have a plus and a minus. If you connect them together, right, you're going to have electric current. So you have electric current from the plus to minus. What is nice about it is that you can control the time. You can have a burst, a huge burst during a very small amount of time, or you have a small burst during a longer amount of time. Remember, because energy is power times time. Okay? So that's a capacitor. Like you have the same thing here. That's a capacitor. You have plus on one side and you have minus on the other side. If you get too close to each other, then the electric field will bring them together and you have an electric current. So there is a discharge. This is called discharging the capacitor, right? So to connect to your question, to go back to your question, in a spark, and that's a Tesla coil, you have a battery, you're going to charge your capacitor. So one is plus, the other one is minus. It's like a defibrillator. And then you're going to discharge it in a coil, right? And a coil has the property to burn out the same amount of energy, but in a very high voltage. So a capacitor can burp out energy as a very high current. A coil can burp out energy as a very high voltage. And because you have a very high voltage, you're going to make a spark. Same thing when you rub your feet against the carpet, you touch the knob, you make a spark because you are at a very high voltage, the knob is at the ground, so you make a spark because you ionize the air and there is a breakdown of the electric field. In addition to that, in a Tesla coil, you have two coils. And if you have two coils, a primary coil and a secondary coil, it's going to be a transformer and you can step up. Okay, so a Tesla coil is two things combined. You have the capacitor and the transformer, and you can create a very high voltage and you can make spark. Does that answer your question? Okay, so you can you can look it up. Tesla coil. It was a genius invention. Very, very smart invention. But now I'm lost. I don't know where I am. I'm here. Okay. So remember the linear. This is a capacitor, by the way. You have two plates. Okay. It's going to be called a parallel plate capacitor. So one here will be connected to the positive terminal of a battery. This plate here will be connected to a negative terminal of the battery. So this is going to be charged positively. That's going to be charged negatively. So you're going to have an electric field. Each plus goes to a minus here. Between you have an electric field. So if you put a proton in between those plates, what's going to happen to the proton is going to go with the flow. So it's gonna accelerate, right? So we talk about that when we talk about linear accelerator. It's the same thing. You have plus here, you have minus there. It's connected to a power supply. Okay, plus is connected to the positive terminal of the battery. Minus will be the negative terminal of the battery. So you're going to have an electric field in between those two electrodes. If you put a ion here, so a proton, the proton will accelerate, and you can speed it up and speed it up and speed it up, and then you can target the tumor. We talk about that, right? Same thing here. You have a cathode here and anode. You have an electric field between the plus and the minus, but now electrons, they will accelerate in the opposite direction because electron go against the electric field, and then they will crash, and all that kinetic energy will turn into X-rays, radiation. So you start with electric potential energy. Remember, voltage is the energy for 1 coulomb, to kinetic energy, and then to radiation. Is that clear? So we did that, we talked about that. So here, come back. Okay, so plus to minus. So what's the question here? Let's try to answer the question. So you have the electric field, 1000 Newton per coulomb between those two plates. Are the line, do you see that the line, they get close to each other and then they go farther away, or they're always equidistant?
Say that again?
Are those lines, are they equidistant from each other about? Yeah, so it means it's a uniform electric field. Between those two plates, the electric field has a constant magnitude and a constant direction. So the electric field between those two plates is 1000 Newton per coulomb. And you have a charge here of 4 microcoulomb. So what's going to happen to it? So it's like a linear accelerator, right? So here you have the electric field is 1000 Newton per coulomb. What does it mean? It means if you have 1 coulomb of charge here, it will be acted upon by a force of 1000 Newton. So here it says, I make a little hole here, and here I have a charge, and that charge here is 5 microcoulomb. So what's going to happen to it? Is it going to sit here, or is it going to accelerate? It's going to accelerate, right? It's going to move with the stream here. It's going to be acted by an electric force. And that electric force is what? Yeah, so it's going to be the charge times 1000, right? For 1 coulomb, you have 1000 Newton. So for that much charge, you multiply. Does it make sense? Okay, so the electric force will be 4 times 10 to the negative 6 times 1000 Newton. Yeah.
Question. Instead of in coulombs, it was in nanocoulombs. What would be the smaller for that?
Nanocoulomb or micro?
Microcoulomb.
Micro is 10 to the negative 6. Nano is 10 to the negative 9. Milli is called, it's 10 to the negative 3. Kilo is 10 to the third. Okay, so what do you get here? It's going to be 4 times 10 to the negative 3. Newton, right? And remember Newton's second law, if there is a force, that means you have an acceleration. So it's gonna speed up. So what is it called? It's called the linear accelerator. And you use that a lot in nuclear medicine. Even for a PET scan, you're gonna use a linear accelerator or an accelerator, yes. Parallel plate capacitor. Or it works too, like if you, as long as you have a plus and a minus here, and you connect to two electrodes, that's going to be about the same. You're going to have an electric field in between. So if you have a charge, it's going to accelerate. So you need a voltage to accelerate a charge. That means the electric potential energy is going to turn into kinetic energy. So to find the acceleration, I will have to do force divided by the mass. Is that clear? So how do I charge? I just have to connect this to a battery, and then once it's charged, I have a voltmeter, and I can find the voltage. And remember from last unit, the voltage is just the energy of the charge per 1 coulomb. For 1 coulomb, how much potential energy does it have? Okay, so just a review from. So you see that the electric field here, what is it trying to do? It's trying to discharge it, right? But it can't. Unless it's strong enough, it becomes very, very strong. Then you have lightning, like I have in my plasma dome or plasma ball. Then you can have a breakdown. Otherwise, it's just there. It's storing energy. Now, to get a plus on one side and a minus on the other side, you have to do work. The work has to be done by the power supply. You need to get energy from the power supply to put plus on one side, minus on the other side. And where did that energy go? It went into the electric field. Okay, it's a way to store energy. Okay, so we have an equation. When you have a parallel plate capacitor, so two plates here, one is charged negatively, the other one is charged positively, so maybe you connect that to a battery, like a car battery, okay, so that will be the plus, that's going to be the minus, and now it's charged. You have an electric field in between those plates, like we have seen. Now you have an equation, easy equation, that will connect the voltage between the plate, the electric field, inside here, where the energy is stored, and the distance between the two plates. Okay? So if you want to try to answer the question, it's like a particle accelerator, right? So maybe at some point I connect that to a power supply. This one becomes positively charged, this one becomes negatively charged. If I look at the voltage here, so I have a voltage between the plates. Let's say this one could be thought as being the ground. So that will be high up. Imagine like it's higher up, works like height. The voltage is the energy per coulomb. And in between, I have an electric field. The distance here is d, and you have that equation there. Because you want to do this one? So 2 centimeters, so the distance here is 2 centimeters, right? So try to do it. So it's going to be 0.02 meters. Has a potential of 100 volt. So that means, imagine this is 100 volt relative to, it's always relative to, okay? Remember, voltage is a property of 2 points. So 100 volt relative to this here, which is the ground. So find the electric field. So they try to trick you, to confuse you, because they say find the electric field in the middle. But the electric field is the same everywhere. So it doesn't matter if you're looking at the middle, if you're looking here or there, the electric field is everywhere the same. So this is just to trick students here, to confuse students. So what do you find? 5,000. So it's going to be 100 divided by 0.02. So divide by 2. And then you multiply by 100 Newton per Coulomb. Okay, so it's a very simple equation. There is nothing to it. Okay, let's try to do this one. So it's a particle accelerator. Say this one is negative charge. So that could be the cathode. That will be the anode. So this is positive, this is negative. There is no conducting wire in between, right? It's just air that you have in between. Or you can have plasma, for example, and you put an electron here. The electron is going to go where? To the left or to the right? To the right, because it always wants to go against the electric field. Counter flow, right? So counter flux. So it's going against the electric field. So it's going to accelerate. Okay, so you are making an electron going faster, and I don't know what they're asking. Can you read here? Okay, find the acceleration. And you have the electric field. So what do we have? We have the charge of an electron, which is 1.6 times 10 to the negative 19 Coulomb. The notation is E. And you have the electric field, which is 2.5 times 10 to the 4 Newton per Coulomb. So it's going to be acted upon by a force. It's like gravity, right? Except it's instead of falling down, it's doing the opposite. Okay, it wants to go to the plus, to lower its potential energy. So what's going to be the force? It's going to be QE, right? So it's going to be 2.5 times 10 to the 4 times E. We are not going to worry right now, it's just the magnitude, okay? Because of course it's supposed to be a negative charge here. So what do you get? 4, negative 15. Did you all get that? 4 times 10 to negative 15 Newton. Don't stare, do it, okay? If you stare, it's not going to help you. And then you can find the acceleration, which is the force divided by the mass. So it's going to be 4 times 10 to the negative 15. And the mass of an electron, you have to be very careful to frame the denominator here. The mass of an electron is 9.11 times 10 to the negative 31. So what do you get? There's a mistake? Is that right? Minus 15, enter, you divide by, open the parenthesis, 9.11 times 10 to the negative 31. Did you get that? Or I did a mistake? Did you get that? You have to do it, okay? Negative 31. Did you get that? Okay, so acceleration is 4.4 times 10 to the 15.
What's under 10?
Mass. Acceleration is force divided by the mass, right? So then they ask you to find the final speed here. And let's say initial speed equals 0. So you have two ways to do it. You have two ways to do it. Yes. Yes. That's here. Huh? Okay. 9.11 times 10 to the negative 31. The mass of a proton is 1.67 times 10 to the negative 27. So the mass here between the electron and the proton, there is a factor of 2000. So the electron is 2000 times less massive than the proton. That's why when you have the periodic table, you don't count the electrons. Is that clear? So how if I use conservation of energy, I want to try that. How can I find? Do I have the voltage? I can figure out the voltage. Oh, they don't give me the distance though. Let's say I know the distance between here and there. Let's say the distance is, I don't know, 10 centimeters. I'm just making things up. The distance is 10 centimeters. You have two ways to find the final speed here. Any idea? We can use conservation of energy. So the kinematics, the conservation of, so the kinematic energy is 1/2 the mass times the speed squared, right? Because you start with a speed of 0, right? But that kinetic energy, oh, you're talking about kinematics? Yeah, you could have used kinematics. So if you use kinematics, that's good. You can say V squared equals initial square plus 2 times the acceleration times the distance, right? And initial velocity equals 0. You have the acceleration and you have the distance, so you can figure out the final speed using kinematics, you're right. Now, if I want to use conservation of energy, let's say I'm going to find the voltage. That will be the energy for 1 coulomb. How can I find the energy of an electron here? Let's say you have the voltage. Voltage is for 1 coulomb. Voltage is the energy for 1 coulomb. So if you have a charge of Q, the potential energy is going to be QV. Does it make sense? This is for 1 coulomb. So if you have that much of coulomb, the potential energy is going to be QV. And that potential energy is going to be converted to kinetic energy. And it should be this equation there. Turns out that this equation and that equation, if you massage them, they are exactly the same. That kinematic equation comes from the conservation of energy. So the same way, remember from physics 1, we have, that was the last part of physics 1, mgh equals the change in kinetic energy, mgh equals 1/2 mv squared. The same thing here. So that will be potential energy and that will be kinetic energy. So we're going to do examples now. Is that clear? So you have electric potential energy and you have gravitational potential energy. So if you take a potato, here that's my potato, it's above the ground, it has gravitational potential energy. If I let go, it's going to go into kinetic energy. Okay, and energy is conserved if you do not have friction in volt. Okay, so that's what it says. Potential energy equals Q delta V. And energy is always conserved. So you can have gravitational potential energy, you can have elastic potential energy, you can have electric potential energy, and you have linear kinetic energy, and you have rotational kinetic energy. Okay. Let's try to do number 2. So talk to each other, help each other. There is TMI here, okay? Just to confuse the students, there is TMI. So first you identify your quantities. So here it says microcoulomb. So what kind of physical quantity this is? A charge, right? So right away I'm going to translate that as 5 micro is 10 to the negative 6 coulomb. Well, that's the speed. We're going to see if we're going to use it or not. So here, you see, volt. So that's going to be a delta V. What is delta V from test 1? Remember, it's the energy for 1 coulomb relative to the ground. Okay, so it means this is the ground, and here it has an energy of 500 joule. For 1 coulomb, I have 1 coulomb of charge. That's going to be how much energy it has relative to the ground. So can you think about how much kinetic energy it can gain? So I am at the same level here, but instead of having 1 coulomb of charge, how much energy I'm going to have relative to the ground? It's going to be 5 times 10 to the negative 6 times 500. Okay, if you remember from what we have learned, what's the meaning of a voltage? A voltage is a potential energy. It works like gravitational potential energy. So it means that if you take 1 coulomb of charge, will be like 1 kilogram, okay? You raise it higher up relative to the ground, it's going to have 500 joule. So if you have that much of charge, you just multiply. It makes sense? That's how much joule it is here, at that level here, relative to the ground. It's always relative to the ground. So can you do the computation? So between them, by the way, of course, you're going to have an electric field here. So that charge here is going to accelerate. It's going to be pulled down to a lower level of energy by the electric field. Okay, you have a force here, an electric force. And all that potential energy is going to be turned into kinetic energy. So the force is the same because you have the same, the electric field does not change. So all that potential energy is going to turn into kinetic energy. So how much potential energy do I have to begin with? Yes. So it's going to be what? 25 times 10 to the minus 4 joule. Is that clear? It's like finding gravitational potential energy, the same thing. That's how much potential energy do you have here at 500 volt. All that is going to be converted into kinetic energy. So how do I answer the question? How much kinetic energy does this particle gain during the period of the acceleration? What is the answer? Yeah, so it's going to be that answer there, right? So they try to confuse you because they give you the initial speed. But we don't care. We just want to know the change in kinetic energy. What we can do is, like we did last semester, we can say the change in kinetic energy is the 0.5, the mass, times the final speed square minus the initial speed square. So we have how much kinetic energy did it gain? So 10 to the negative 3 equals 0.5 the mass. Maybe I have the mass and I have the initial speed. So now I can find the final speed. But if the question is just what is the change in kinetic energy, that's just the answer. Is that clear for everyone? So potential energy turns into kinetic energy, like in physics 1, except the equation is Q delta V. Okay, so let's try to do this one. Don't sleep. Do it. Not because it's too dark here, okay? Put your... Someone told me it was too dark. Is that better? Can you do it? Everyone is tired. I think that should have been the spring break now. Okay, you doing the computation? Form rest. Okay, let's translate. Form rest means initial velocity equals 0. Potential. Okay, that means that's gonna be my delta V. So it's going for a potential difference, right? From 1500. So an electron will do the opposite, right? So an electron, if this is minus here, this is plus here. Imagine this is 1500 relative to here, which is 0. An electron wants to do the opposite, okay? So this is an electron, it's negative, it wants to go to the plus. So it's going up the potential. A proton, we do the opposite, it's going down the potential. The goal is the same. It's always the same in nature, it's always to lower the level of energy. As I said, students usually they come here, they always sit at the same spot because you save energy, right? If you start to think, should I sit here? This guy looks like not right, so maybe I should sit there. No, it's not right. Too much light, like Sheldon, too much draft, not enough light. It's tiring. So you always go back to the same place. So here it's the same thing. It wants to lower its level of energy. Okay, so we have QV equals the change in kinetic energy, so 1/2 the mass, final speed minus initial speed. Okay, initial velocity is 0. So then it's just math, right? You plug it in. So 1.6 times 10 to the negative 19. Then voltage is 1500 equals 0.5 times the mass. Okay, the final speed, that's what you are trying to find. Initial speed is 0. So that's the conservation of energy. This is potential energy, that's kinetic energy. Okay, so try to do it to make sure you know how to use your TI. So I'm going to start here. So 1.6 times 10 to the 19, okay, times 1500, so times 1500, okay, divide by 0.5, so I divide by 0.5, enter, and then divide, I open the parenthesis, always open the parentheses, times 10 to the negative 31st, enter. That's going to be your v square. And then you take the square root of that, so you go second square. You call back the previous answer here, and you get 1, 2, 3, 4, 5, 6, 7. Yeah. I use this one. Potential energy equals the change in kinetic energy. Right? And then I'm solving for v square. Are you with me? You're not falling asleep over there? So 1, 2, 3, 4, 5, 6, 7. So 2.3 times 10 to the 7. Everyone? Don't just copy, okay? You have to make sure you get the same answers. Okay, so the answer is A. Okay? Conclusion? Voltage, again, like we studied that in the first unit. Voltage is energy, potential energy per coulomb for 1 coulomb. Okay, so 12-volt battery means for each coulomb you have 12 joule. If you have 2 coulomb, that will be 24 joule. So that's the electric potential energy. In a linear accelerator, that potential energy can be turned into kinetic energy. And if you have this kinetic energy, if you have the electron crash into a heavy metal, all that kinetic energy can be turned into X-rays, because X-rays, of course, do have energy. So it's called radiation, radiative energy. So this one is easy. They try to trick you because the multiple choices had EV. Do you remember EV is also a unit for energy. E is just the charge of an electron. So if you have an electron going through 1 volt and its charge is E, what's going to be its potential energy? EV, just one EV, okay? It depends on the unit. Okay, so the potential energy is the charge times the voltage. If the charge is in coulomb and the voltage is in volt, then the unit for energy is going to be joule. If the charge is in E, so how many electrons or how many protons, the voltage is in volt, then the unit will be EV. Okay? So remember, we did that plus unit. If you have 12 volt, that means that each electron leaving the negative terminal will have an energy of 12 EV, because that's the charge, that's the voltage. The charge is E, the voltage is 12, so it's going to be 12 EV. Okay? If you are doing chemistry, any chemical reaction always involve a few EV. It's very, very small, a few EV. If you are doing nuclear medicine, so then we are talking about mega EV, okay? Mega, right? Mega is 10 to the 6 or more. If you are talking about an accelerator, particle accelerator. Okay, so let's try to do this one. It's easy. You have a positive charge here at A, and it has no speed to begin with. It has a charge, and they tell you that the point A has a voltage 25 greater than at point B. And they ask you to find the speed. So what does it mean? It means that at that point here, it's going to be 25 volt, right? And you can imagine if it's 25 volt higher than here, this is going to be 0 volt. Okay, so that you imagine this is the ground, this is 25 volt, that means 25 joule per coulomb. That means each coulomb of charge here has an energy of 25 joule. And it wants to go down the potential because it's a positive charge. Positive charge always wants to go down the potential. Imagine this is plus, you can imagine this is plus, this is minus, so it wants to go from plus to minus, right? So all that potential energy it has here is going to be turned into kinetic energy. And it says the initial velocity is 0. It's the same thing here. So potential energy is going to be turned into kinetic energy. It's accelerating. So it's going to be what? U delta V equals 0.5 the mass, final speed minus initial speed. But initial is 0. So how much you get? So 3 times 10 to the negative 5. The potential is 25 equals 0.5. The mass is given. So 1.8 times 10 to the negative 5. And the final speed, that's what you want. So you're doing it? So you can do that with the TI 3 times 10 to the negative 5. Okay, close the parenthesis, 25. Okay, divide by, open the parenthesis, 0.5. Go step by step. Divide by, open the parenthesis again, 1.8 times 10 to the negative 5. Close the parenthesis and you take the square root. You get 9.1. Did you get that? Make sure you do it step by step when you have scientific notation. It can be tricky. If you don't put parentheses, there is something called pandas, and it's going to divide, and then it thinks that next it has to multiply. So you really have to not forget your parentheses. So the answer is 9.1 meter per second. Yes? So imagine always when you have high potential, here low potential. The positive charge wants to go from where to where? High potential to low potential or low potential to high potential? Very good. High potential to low potential. Does it make sense? A negative charge is counterintuitive. It wants to do the opposite. It wants to go from low potential to high potential. So you might think it's weird, but look, if it's negative, it wants to go to the plus. So the only way to lower the energy level for a positive charge is to go from high potential to low potential. A negative charge wants to lower its potential energy, level of energy, it will go from low potential to high potential. Okay? So here, if I do the opposite, everything is symmetric. What's going to happen here? If you have a negative charge, it's the same charge, but now it's negative. I place it here, what's going to happen to it? Is it going to sit there? Is it going to move to the right? Or is it going to go up the potential? Up the potential. Okay, it will have the same potential energy in magnitude and it's going to turn into kinetic energy. So the speed here will be the same. So it's going to be 9.1 meter per second. Is that clear? Right? So if you take, if I go back to here, what can I do? I can take a charge here. That's my charge. I'm tired of that electric field. So cool, right? And so if I go here close to the positive charge, I'm going to have high potential. And as I move away, you see that the potential is getting lower as I go to the ground, and very far away, it's going to be the ground. So you can think of potential as height. So if you take a positive charge, it wants to go from high potential to low potential. Okay? If I have a negative, that's too bad. They should show me a negative charge. No, they should have a charge like this, but
Error.
yes, exactly. So if you have a negative sensor, then it will be the opposite. It should be. Oh yeah, if I put a negative charge here, if I put a negative charge, it's going to be pushed toward, right? Because now the ground here is going to be higher than there. So the potential here is going to be negative, 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 and there it's going to be almost zero, very far away. So a positive charge wants to go from low potential to high potential. It wants to climb the potential. A negative charge will do exactly the opposite. When you say very far away, it just means ground. Okay? So if I have my plasma ball here, I go from 1000 volt to 0 volt. But if I don't touch it here, I will go step by step, right? 1000 and then multiplied by 2, that's going to be 500 and 250, that's going down by steps. We're going to see it's an inverse law. So multiply the distance by 2, the voltage is divided by 2. You multiply distance by 3, the voltage is divided by 3. You multiply the distance by 4, it's divided by 4. So if I'm here, I am at 1000. I multiply distance by 2, so it's going to be what? Divide by 2.
4.
No, we start with 1000, right? The distance is multiplied by 2, the voltage is divided by 2. So 1000 divided by 2 is 500 volts here. It's inversely proportional. It's not like the electric field. The potential is inversely proportional. Multiplied by 3 is going to be 1000 divided by 3. Multiplied by 4 is going to be 250. So we're going to see that. By the way, since someone asked, I don't know if she's here. Someone who was in my office before. No, she's not here. For those preparing the MCAT, this is a very nice book. It's called Johnson and Cotnell. I had this book, at the beginning of my slides. I just found it. I don't know if it's a legit website. You have to check. But you see, you can find it for very cheap, like saving $231 is not bad. But anyway, my point is that Johnson and Cotnell is a very good if you want to prepare the MCAT. They have very good solution. And thrift books is a very good way to save money. If you want to save money, so if you don't want to save money, don't have to. Application, since you are in a lot of you are in health science or biology, you can use it's called DNA fingerprint. So what's happened here? You have DNA segments, right? And they're gonna be negatively charged. So they charge them negatively. So this is the negative cathode, that's going to be the positive anode. So this is positive here, it's going to be negative. And you charge your molecules of DNA. So what's going to happen to them?
Charge the negative.
I charge the pieces of DNA negatively. So this is negative here. Those little DNA fragments I managed to put a little negative charge on them.
Track opposite.
Okay, so that means this here, it's like a parallel capacitor. So this is plus and this is minus. And those DNA fragments are charged negatively. Are they going to stay here or they going to move to the right? They're gonna move to the right? They're gonna have force acting on them, F equals QE. So they want to have an acceleration. Which one will have more acceleration, the big one or the small one? Small one, okay, less inertia, more acceleration, right? So you have the acceleration equals QE over M. However, you have some kind of gelatin here, right? Gel. So what's going to happen to them? So they want to move to the right, but they are placed in some kind of, it's like oily, it's not oil, it's like a gel. So they will be acted upon by two forces, right? So it's kind of friction. So you have a piece of DNA, it's negatively charged, so it's going to be pulled to the right by the electric force, right? Because you have an electric field in between, but now you have what is called a viscous drag, which is exactly the same. So I was looking on the internet trying to find a way for you to understand, and I had no idea that you had such things. Did you know that? To exercise? Do you know that that thing is a real thing? So yeah, so what's gonna happen? You push on the ground, the ground push back on you, and there is a drag force here. But as you're gonna move faster and faster and faster, the drag force is increasing. Until what? Until the drag force equals to your pushing force, right? The thrust. So when the thrust equals the drag, what's gonna happen? Do you have any acceleration? No, you reach what it's called terminal speed. Okay, you can't. You have so much, engine in your body. You cannot go faster than that. So you have reached terminal speed. So here it's the same thing. Those little fragments, they are acted by an electric force that will not change. It's constant. However, the drag that they will be acted upon, because there is some viscous thing here, is going to increase until they reach the terminal speed. Which one will reach their terminal speed the faster?
Recording one.
Which one will arrive first?
All
Smaller one. The large fragment will reach their terminal speed later and lag behind. So the small one will arrive first and the large one will drag behind. And then you stop, everything freezes. So then you can separate the small fragment from the big fragment. Isn't that interesting? Isn't that cool? So you have you can look up online to learn about that. It's called DNA fingerprint. Okay, so someone told me it's a catfish. It's not a catfish, it's an electric fish. They live in South America somewhere. You are the one who are into marine biology. So I think it's a freshwater fish. And interesting about that is that it's gonna produce an electric field from plus. So it has some kind of uh, charge separation between this part of the body, that part of the body. So here you're going to have plus, here you have minus, you're going to have an electric field between plus and minus. So what's going to happen if you put something that is alive? Is it a conductor or not a conductor? It is a conductor, right? So because it's a conductor, all the minus will go on one side and the plus will go on the other side. So it will make the electric field stronger. Right? You see how the electric field lines are closer to each other? I have a picture. Let me, so you can understand. If I can find. here. So if you place a conductor inside an electric field, what's going to happen? Here on that side, you're going to have all the electrons, because remember, in a conductor, electrons can move. So all the electrons will go on one side, and the plus here will go on the other side. So you're going to have this configuration, and it will make the electric field stronger. So the fish will know that there is something to eat in the surrounding. If it's alive and it doesn't seem too big, okay, I'm going to eat it, right? It's not very picky. It seems to be alive since it's a conductor, so it can eat. I think they live in muddy water. That's why maybe they don't see well, or they don't have good eyesight. Yes. I have no idea what it is. It says it's a eel. It's something electric. I don't think it's a eel. Eel doesn't have like an elephant nose here. You tell me, okay? You are in marine biology or biology, okay? You tell me what kind of fish this is. Maybe I'll give you extra credit. It's some kind of weird fish for sure. Now, if you have a non-conductive object here, like a stone, what's going to happen? It's an insulator. It's not conducting. So what's going to happen? It's going to be polarized, and the opposite is going to happen. The electric field will be pushed away. Yeah.
They're actually called elephant fishes.
They are elephant fishes?
Term, it's like what they're like.
Oh, where do they live?
In Africa.
Africa. Fresh water? Oh, you tell me. Send me an email so I'll give you extra credit. What's your name? Chanel. Yes. Okay, so anyway, if you have something that is not a conductor, which means it's an insulator, which means it's not alive, so then it's going to change the configuration of the electric field from the plus to the minus, so it will know that it should not eat it, right? So it's some kind of radar, but instead of pinging, like sending a ping with radio waves, it's using static electric field. Isn't that cool? So I guess you should look into that. Yeah. Why does it need to use an electric field? Maybe it's blind or something. I don't know. Another application for electric field, of course, is the DNA. The two what it's called, the strands. It's called strand. What do we call those things here? Strands. Okay, those strands, they are connected with each other with an electric force, right? So A goes with T, C goes with G, and so forth and so on. You know better than me. So these are electric forces. Here, the way the DNA will replicate itself, a lot of electric force involved, because oxygen wants to be with hydrogen, because this one takes electrons away from the carbon. Hydrogen is always willing, it is a giver, it will always give away its electron. So nitrogen took the electron, so this one is positive, this one is negative, so they are attracted to each other, so you have an electric force between them. Right, what else? So again, DNA stuff. Okay, that we discussed, that the way electrolyte can go from outside the cells, inside the cells, it can move because you apply a voltage, because there is a voltage between plus outside and minus inside, or maybe it's the opposite here. Here is plus, minus, you have more plus here than, and here you have more minus. So there will be a voltage between the inside of the cell, outside of the cell, so you're going to have an electric field. If you have an electric field, then the electrolyte will be pulled outside or inside, outside or inside. Okay, so the cell membrane has a voltage applied across it, so that way the cells can move electrolyte in or out. And then I was looking at a paper which I could not pass the 3 first sentences. If you can, if you are in medicine, good for you. But I read that you have a new technology because some very serious, we are talking about very, very serious disease that target that has to do with the brain, like mental health issues that has to do with the brain. You want to deliver the drug to the brain, and it's very hard to do because the drugs don't want to cross the barrier between the blood and the brain, right? It's like a barrier that is very hard to cross. However, if you have the drug inside what it's called the lipid nanoparticle, okay, I learned that. It's going to be charged, so you charge it, right? So you charge that nanoparticle, it's a lipid nanoparticle. So first of all, it's a lipid. Lipid means fat, and the brain likes fat because it's all the neurons in the brain, it's made of cholesterol, so you need the fat, you need the cholesterol, of course. So it's going to go into the brain. Once it's inside the brain, because those nanoparticles are charged, then it will be acted upon the electric field that you have between the outside of the cell and the inside of the cell. So they are working on that. But it's called gene therapy, if I understood. Of course, it has a lot of side effects, but this is done only when you have a very serious disease. So you have to balance out risk and benefit, and usually it's for people who need that drug to be delivered, right? Isn't that interesting? So I have the article here, so if you can pass, very hard for me to understand. So I understood that part, so if you can understand the whole thing, good for you. It's very advanced. So I thought that was interesting. It's a new technology that is being developed. It's called lipid nanotechnology, particle technology. Okay, another way to apply electrostatics, it's in the Xerox machine. So that's not a new technology, that's an old technology. So if you want to use your copy machine, the way it works, it has a drum, right? It's made of a semiconductor like selenium, and it's positively charged. So everything is positive, 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 positive. This is the ground. And then here on the top of the machine, for example, you have the 3 and you have light. You see when you close your copy machine, it's a light on. That light is going to kick all the electrons out or all the charge out. It's called the photoelectric effect. And what is left behind is that 3 here. So it's made of positive charge. So now you have your 3, which is traced with positive charge. And then the drum goes around. And here you have the tuner, which is made of dust, negative charge, so plus and minus, they attract each other. So now it's made of powder. That's why you don't want to put your finger in, and then it's heated up so it sticks. So that's how it works. Isn't that amazing? Do you understand any question? I mean, it's easy to understand. The only thing that is you have to know is that light kick out charges, right? That was Einstein's discovery. It's called photoelectric effect. The light can kick out charges, so it's kicking out charges here except in the shadow, so that's why you have positive 3 here left. Okay, another application, electrostatics. I don't know if you're still using it, but a few years ago it was everyone used to have that. It's like a reader, it's like a book, and it's also using electrostatic. One side is negative charge, the other side is positive charge. So those little beads inside here, each pixel has this little container, and this one is, those little beads here are negative charge, so it's going to be attracted to plus and repelled by minus. So if you put a minus here, the bead is going to go up and you see white. If it's positive charge at the bottom, then you see blue. That's how it's done. What else? Oh, more math. Yay. Okay, let's just review. So let's review. You can help each other. So if you have a point charge, just a charge, and you have 2 times 10 to the negative 9 coulomb. And so that's my charge here. So I take a positive charge here, have a positive charge, and I'm looking at the electric field here at a given distance. So you see that at a given distance, the electric field is the same, and it obeys an inverse square law. If you multiply the distance by 2, the electric field is divided by 4, right? So you have a positive charge, the charge is given, and you want to find the electric field here at that point there. So it's just a review. So you have that point here, you have the distance r, and you want to find the electric field. And I just remind you that if you want to find the electric field, you just put 1 coulomb of charge here, and what's going to be the force here, right? The force will be, it's like Coulomb's law. Okay, so you're just applying Coulomb's law for 1 coulomb of charge. That will be the magnitude of the electric field. Okay, so just a review. So the electric field is like the Coulomb's law force on 1 coulomb, and it's an inverse square law. So the only challenge here is to convert. And it says, what does it say? 5 millimeter? Is that a 5? Okay, it's a 5. So 5 is 1,000 with a TH. Hey, look what you can do, like your algebra skill. You say bye. Because 9 minus 9 is 0, 10 to the 0 is 1. 9 times 2 is 18. 5 times 10 to the negative 3. So what you get? There was 1,000 for sure. Because there is a... Do you get that? Do you get that? You have to be careful when you divide. Always put a parenthesis. If you don't put the parenthesis, what it's going to do? It's going to divide by 5, and then it's going to multiply by 10 to the negative 3, which is like dividing by 1,000. So when you divide, make sure you frame the denominator. Frame it.
So this square is going to be for
Oh, yo. Oh, yeah. I was doing on purpose to see if someone is noticing. Thank you. Okay, so I have to divide more, okay? So it's going to be 18 divided by 5 times 10 to negative 3. Thank you for noticing. No, I have this. Do you get that now? 1, 2, 3, 4, 5. So it's going to be 7.2 times 10 to the 5 Newton per Coulomb. Yes? Okay, what force? So if you have a charge, it's a negative charge. What's going to be the force? The force will be equals to QE. Okay, so now I have a negative charge here, so that's going to be a negative charge. So it's going to go against the electric field. It's going to move in this direction, and the force is going to be 0.25 times 10 to the negative 6 times 7.25 times 10 to the 5 in magnitude, okay? I know that it's going to move to the left here because it's negative. Is that right? So I multiply by the charge, which is 0.25 times 10 to the negative 6. That's micro. And you get 2.5. No, I didn't multiply. So what do you get? 0.25 times 10 to the negative 6. Enter times 7.25 times 10 to the 5. Okay, 0.18. Is that right? 0.18 Newton. Okay. So do the rest for Tuesday as an exercise. So that way, next time we can move to the capacitor. We need to do the voltage. The voltage won't take so much time. We're almost done. Okay, for those who are late, we said that the